Good morning. Good morning. Okay, I'm recording. Basically, what I'll do is start the thing. So basically, what I'm going to do now is switch to the thing and just go just on the basis of the PowerPoint and talk about what essentially going forward as if I was teaching it. So basically, join in when you can. We did have one person. I'll see about fixing. So she's here. Okay, so what I'm going to do now is go to the slides, and we'll join as people get here. But basically, what I'm going to do first is to open up the thing and talk about where we're going with this. The first part is to refresh the kinetic molecular theory of gases. And so what I'm going to do is share the screen with you now, and we'll start from here. Okay, here we got the kinetic molecular theory of gases here. Essentially, what I'm going to do now is erase what's on the thing. And kinetic molecular theory of gases, essentially, it consists of these. A gas composed of molecules are separated from each other by distances farther than their own dimensions. The molecules can be considered to be points. In other words, they have possess mass, but they have negligible volume. You've already seen that. You will see that in the lab this week. The gas molecules are in constant motion in random directions. They frequently collide with one another. The collisions among molecules are perfectly elastic. Gas molecules exert neither attractive nor repulsive forces on one another. And then the average kinetic energy of the molecules is proportional to the temperature of the gases in kelvins. So basically, all the gas laws come from these set of rules of the kinetic molecular theory. And the kinetic energy is related to, this is the kinetic energy related to the temperature of the gas, which is in the velocity of the molecule of atoms or molecules. Because if you remember what the definition of kinetic energy is, that is 1/2 mv squared. So in this case, you got 1/2 m, and then the root mean squared things of velocity of the molecules there. Essentially, what it pushes for is the compressibility of gases. You have empty space in between. You can push them together. The velocity between more molecules, more collisions. You get Boyle's law from that. The pressure is proportional to the collision rate with the wall. The collision rate is proportional to the number density, and the number density is proportional to 1 over the volume. And the pressure is proportional to the 1 over the volume. Charles' law and Gay-Lussac's, the pressure is proportional to the collision rate with the wall. You increase the pressure, more collisions. Collision rate and average kinetic energy of gas molecules. So you got the velocity, higher the velocity of the molecules, the more collisions. And the average kinetic energy is proportional to temperature. And pressure is proportional to temperature. That's the Gay-Lussac's law. Avogadro's law, the pressure is proportional to the collision rate with the wall. Collision rate is proportional to the number density. The number density is proportional to the number of moles. The pressure is proportional to the number of moles. And then Dalton's law of partial pressures, which you're doing in the lab this week. The pressure exerted by one type of molecule is affected by the presence of another gas. So you add the two different things together. And basically what you got to have to, like this week, is the pressure of the oxygen plus the pressure of the water vapor equals 1 atmosphere in your vessel. So that's the key thing that you're dealing with in this week's lab. Here's the distribution of speeds at different temperatures, and then 3 different gases at the same temperature. And so there's a root mean squared velocity there related to the mass of the molar mass of the gas. Gas diffusion, essentially you have those together, gradual mixing of them. Okay, and they will meet in the middle. And then gas diffusion is the process by which a gas under pressure escapes from one compartment to another by passing through a small opening. Nickel forms a gaseous compound. What is the value of X under the same conditions? If methane effuses 3.3 times faster than the compound, essentially you have it like that. And then that would be a sample problem you might have to do. Now the deviations from ideal behavior, essentially the ideal behavior has to do with no attractive or repulsive forces, but with real gases there are. And so basically you've got to adjust for this. This is for the volume of the molecules, volume of the molecules or atoms, okay? And this would be for the adjustment of the, this is the volume of the molecules here, adjustment, and this is the adjustment of the pressure related to the mass of the particles. You also got intermolecular interactions. So if you have a gas like H2O, you'll get hydrogen bonding. Okay, and with ammonia, you'll also get that. So basically, the ammonia looks like this with the 3 hydrogens around it. So basically that is the going for the part with the other material. So that's the introduction to today's lecture, which is going to be on solids and liquids. So if you remember what I was talking about, where the other part, now what we're going to do is talk about the solids and liquids. And so now what I'm going to do is open these up, and we'll talk about intermolecular forces and liquids and solids and how they go from gases. So essentially, we're going to continue the lecture and talk about this today. And I will take two lectures to do this, irrespective of whether we have people or not. But I hope you enjoy it, either if you watch it now with me or later. Intermolecular forces, and this is what I was talking about before. Basically with ice, But basically with ice, you have intermolecular forces. You got water molecules that look like this. This is a negative region, negative. This is a positive region. So these interact with the positive on other molecules like this. So basically they'll orient around each other. And here you have another oxygen over here like this, interacting with the hydrogen. And so these are hydrogen bonds. And if you bring those gas molecules together, you'll get a liquid and then get a solid. Now, there are certain aspects regarding liquids, solids, and gases, and this is called phases. There are 3 phases of matter. Solid, which has low energy. Okay. Liquid, medium energy, and then gas, high energy. So, and you also have plasma, which is different, but we'll talk about that another time. But the phase is the homogeneous in contacts with the other things by a well-defined boundary. And that's important to keep in mind regarding how it works. Okay. So in this case, we have ice and water. 2 phases. The solid phase is ice. The liquid phase is water associated with this. And basically, these are the definitions of the different aspects to gases, liquids, and solids. A gas assumes the volume and shape of its container. Low density, very compressible. Again, mostly empty space. So you have mostly empty space here. Very free motion. Liquid has a definite shape, but has definite volume, but assumes the shape. High density, only slightly compressible. They flow. And then a solid has a definite volume and shape, high density, virtually incompressible, and then they vibrate. So that's the characteristic aspects of each of them. Now, the key thing to understanding how solids, liquids, and gases form is intermolecular forces. So basically, intermolecular forces are attractive forces between molecules, essentially interacting with one another. They hold, intramolecular forces hold atoms together in a molecule. And then contrasting both of them, for example, to get liquid water to gas, liquid to gas requires energy. This is endothermic, okay? And then when intra-bonding, you got to use a certain amount of energy to break the bonds, hydrogen, oxygen bonds in 1 mole of water. That's intramolecular bonding there. So it's different there. What we're dealing with liquids, solids, and gases is essentially the causing the molecules themselves to move and break intermolecular forces and then go. Okay, so basically there's a bunch of measuring of them related to boiling point and melting point, the delta heat of vaporization, and the delta heat of fusion. So essentially this is the boiling point, this is that for this, and that's the way to measure how those things interact regarding the heat required to go from a liquid to a gas. And then here, this would be melting, going from a solid to a liquid. There are features in both of them that's important to keep in mind. And then sublimation, this is going from a solid directly to a gas. So if you have a thing that's like this, you have gas here, a liquid, and then a solid, you could have a bunch of different transitions. The solid to a liquid is melt. Liquid to a gas is boil. Gas to a liquid is condensation. Liquid to a solid is freezing. Gas to a solid is deposition. And then solid to a gas is sublimation. So there are a bunch of different terms associated with the different intermolecular forces between them. Generally, intermolecular forces are much weaker than intramolecular ones. So it's important to keep that in mind too, because intramolecular forces are the ones for chemical bonds. So basically you've got a different matter, you've got a different aspect of features associated with each of them. Now, there's a bunch of different intermolecular forces of which you talked about a little bit last semester, and in the gas part, there's dipole-dipole forces that are attractive forces between molecules. And this would be the orientation of a polar molecule on a solid. If you cause these to move, they will melt. More move, it will melt and go to a liquid. Okay? So in a solid, you cause them to move and break those bonds in between. Essentially, that will cause it to go to a liquid. Those are the interactions there between molecules. They're ion dipole forces between an ion and a polar molecule, and that would be, this is where you have a solution. Okay, so here you've got a solution associated with that. The interaction between water and cations is a weak interaction there, and a stronger one with bigger cations. And then a solution, it'll look like this. So you've got a combination of them all around the center atom, whether it be a sodium atom or whatever else. These are all water molecules. These are in solution. The next intermolecular force is called dispersion forces. And basically you've got attractive forces that arise as a result of temporary dipoles induced in atoms or molecules. An example of that would be, for example, a cation with an induced dipole there, and then a dipole with another induced dipole. And there's a bunch of different examples of those kind of things. So if say, for example, you've got a cation coming in with a particular thing that's not very polar, and that would be like an interaction between a sodium ion and an iodine molecule like this. You'll get some interaction with this, and essentially it'll push it'll cause this interaction between them all that way. Induced dipoles interacting with one another look like this. That'll be easy. That's a weaker bond than the other one. And then dispersion forces, polarizability, there is these, which the electron distribution can be distorted. It increases with a greater number of electrons, more diffuse electron cloud. So basically, it's directly related to the melting point of particular different materials. For example, if you've got interactions between methane, this is a gas, and then you've got carbon tetrabromide, this is a solid, and this is a liquid, this is a liquid, this is a gas, these are gases, and this is also a solid. So essentially, these interactions between each other essentially will force these to kind of be closer together. And that is an example of the intermolecular forces between them. Dispersion forces usually increase with molar mass. Now, what types of intermolecular forces exert between each of the following molecules? Well, if you set it up, if you draw the Lewis dot structure for it, you can see these different molecules here. This will have a positive end and a negative end. And so this would be dipole interactions. Here, with this, essentially there is very little associated with that. And then SO2 will look like this. With things, so it's sort of bent. So it's essentially look like this kind of here with this, and this will kind of flow back and forth. So this will be a more positive side. This will be a negative side associated with that. And so that would be more the dispersions as well. You've got the dipole-dipole forces between the hydrogen bromide. It's nonpolar dispersion forces there. And then with SO2, you have that things. It's polar, so you have dipole-dipole forces, and there are also dispersion forces between them. Hydrogen bonds are very important here. The special dipole-dipole interaction between hydrogen atom and polar NH or OH, FH bond and an electronegative atom. Okay, and so for example, between water molecules, this is the hydrogen bond. This will cause, essentially makes it easy to freeze ice. Okay, and the interactions between ammonia, you can get ammonia ice fairly easily, and then interactions between water and ammonia there. This would be for a solution. And then you've got other examples of these different kinds of hydrogen bonds associated with each. And this is an example of formic acid with water, the different hydrogen bonds that will hold it in place. Now, why is this hydrogen bond considered a special dipole-dipole interaction? Well, basically, is it because of the fact that it will form a special system in this. And with all the stuff that has some hydrogen bonding, the boiling point is higher, even though this is a smaller molecule, but then these other ones, essentially the boiling point is low with this, the small one, H2S, and these other ones. And then as you go higher and higher, the boiling point goes up associated with this, but methane is down here where there's no real interactions, but the hydrogen bonds essentially give this an abnormally thing. And this is what's particularly cool about it, is that with water, it will cause, water expands when it freezes, when freezing. And that's because of the hydrogen bonding. Decreasing molar mass, decreasing boiling point, but then you've got the hydrogen bonding occurring on those other ones. And so basically, if you got greater forces holding it together, if you've got a set of molecules that are gas, okay, and you've got intermolecular forces, that will cause it to go to a liquid if you decrease the temperature enough, or easy to form liquid with pressure. Okay, so basically, if you got ammonia, which is normally a gas at room temperature, you put this under pressure, it's easy to liquefy. Okay, because you're forcing the molecules close to one another. Forcing molecules closer. Okay, so that's important to keep in mind how that works regarding that. Surface tension, the amount of energy required to stretch or increase the surface energy by unit area. But again, this surface tension is related to the intermolecular forces in the liquid. Intermolecular forces with liquid. For example, if you got water molecules here that look like this, this will have a relatively high surface tension because of these interactions. So essentially these water molecules will have a surface tension associated with that. So basically the surface, this is the surface tension holding it all into place. Strong intermolecular forces between them, high surface tension. Cohesion is the intermolecular attraction between like molecules here. And so if you got a system like that, we have mercury, you got cohesion together in there. Adhesion is attraction between unlike molecules there. And that would be like this, pulling up a glass tube. Viscosity is a measure of the fluid's resistance to flow. And basically, the greater the intermolecular forces, the higher the viscosity, higher viscosity. Okay, because you're resisting the flow. Here are some different examples of viscosity associated with this. And basically glycerol has a relatively high viscosity because glycerol looks like this. You've got all sorts of hydrogen bonds associated with this. Okay, and you've got all sorts of hydrogen bonds in between, and that will cause them to kind of interact with one another, interact easily. So it'll resist flow. Strong intermolecular forces, the greater the flow, high viscosity. Water is a unique substance. You got a 3D structure of water here. So basically with water, if you cool it down, it will freeze. And this is with ice. This is ice here, and it will form crystals associated with that. Ice is less dense than water because of that big network. So at minus 20, the density is lower that way there. So basically the density goes down as the water freezes. So it will float. The maximum density is at near 0 degrees Celsius. A crystalline solid possesses rigid, long-range order. In a crystalline solid, they occupy special predictable positions. An amorphous solid does not have a defined arrangement, so crystallines might have a whole lot of molecules all lined up like this, whereas amorphous is all general things with all sorts of things like that. And this is easy to melt. This is a little harder to melt sometimes. But basically, you've got a longer way because you have to, heat will loosen the chains. A unit cell is a basic repeating structural unit of a crystalline solid, and these are examples of unit cells associated with this. So in things, you might have a sodium atom in the middle, and then a bunch of chlorines out on the side with sodium chloride. And that would be the ionic interactions that hold them in the place in the solid. That's called the lattice point. And the lattice points, you can have atoms, molecules, or ions associated with it. Here are some basics unit cells associated with this here. The simple cubic, the tetragonal, the orthorhombic and rhombohedral, monoclinic, triclinic, and such like that, hexagons there. And then 3 types of cubic unit cells. And I highly recommend you read the textbook here when you're interacting with these slides, because the textbook description is much better than I could give you just with a lecture, because it puts it all in context with the different diagrams. Now, the simple cubic cell here, this is one relationship with this. You have one atom or molecule at each point. You've got a center in the middle. It's kind of like putting a whole bunch of basketballs together. And that's a simple cubic arrangement. With a body-centered one, that would be where you've got one in the middle between all those. It's a little more expanded. And an example of that would be like having a sodium atom with a bunch of chlorines all around it, interacting. Okay. And then you got other sodiums around it, the other side. Corner atom, edge centered atom, and face centered atom all look like this. There, you've got a corner atom shared by 8 unit cells, an edge centered atom by 4, and a 2 centered unit cell there. Number of atoms per unit cell, simple cubic. Body centered cubic, and then face centered cubic. The relation between the edge at the radius there, it all depends on the edge. A is the edge length, and then 2 times the radius. With that structure, here the structure is a little bit more complex. And then this is another one. And then you've got different kinds of packing associated with each of these two, hexagonal and cubic packing, where you've got them closest packing connected together like that. That's hexagonal. And then this would be cubic. Exploded views associated with each of them. This is different kind of structures. Now, this is a sample problem that you'd have, and I will, and basically, if we look at the unit cell here, calculate the density of silver. The density is equal to the mass divided by the volume. The volume equals A cubed. So A is 409 picometers cubed, and then that's the volume of one cell. 4 atoms per unit cell in a face-centered cubic. So the mass is 4 silver atoms. gives you how many there are. That's the mass of one silver atom. The density would be like that. You calculate that and you get 10.5 grams per cubic centimeter. How is this arranged? Well, basically they use what's called X-ray crystallography, and they can project what the crystal structure looks like by shining X-rays through it that can enable it to see. And again, this is best understood by the reading of the textbook. Now, most chemistry classes don't go very heavily into the solids and liquids portion that I'm talking about now. I'm not sure how much Dr. Gerhardt and Dr. Powell will be doing on this, but it's important to keep in mind the nature of the different aspects of each associated with this. Now, here's a sample crystal structure example, but I don't think that's going to be asked of you. Okay, so I will stop for today, and basically I'll finish this on Thursday. Hope you like this introduction. Very good. Any questions, please ask me in lecture. Please ask me in the lab. We're done. Thank you.